Hello all, how you doing? Right, so this is going to be the electric circuits overview and revision section, video, whatever you want to call it. You can call it that. Right, okay, so we're going to start out with the single worst formatting ever. Right, this isn't nice, is it? That's nicer. You're thinking, Liam, you could have done this in advance, but no, it wouldn't have been as fun, would it? So, charge and current. Basically, we're just going to go over everything really quickly, the basics, the fundamentals. Do reread the notes that are attached as well, and then do the questions. So, charge and current, you know what these are, but I'm just going to run through them. So, charge, it's a fundamental property, you know that. So that means not only can you not have it, it has to be conserved. It's probably quantized as well, which means basically that, yeah, is going to be a quantum property just as much as it's going to be any other kind of property. But basically, it comes in a small packet, fundamental charge, 1.6 times 10 to the minus 19. Current is measured as the rate of flow of charge, and as such is measured in coulombs per second, right? Its unit is the ampere, and it is defined as a current is measured as 1 ampere when 1 second of charge passes a point in 1 second. And you can reverse engineer that to make the definition for the coulomb, and you could even make the definition for the second, but that'd be weird. But you could if you wanted. Yeah. So then there's the conventionality of current. So the direction of them is a really important factor. It will determine, well, you'll just lose a mark probably, but yeah, it's a factor. So positive to negative, that is conventional flow, right? And that is not because of like some oldie world way of doing it. It is just the convention. It is the way that it is referred to. So when we're talking about current, we're talking about conventional current. The convention is from positive to negative. When we think about it like in physics, we think electron flow, which is negative to positive, but neither's wrong, right? If you move electrons from right to left, you're moving positivity by removing negativity. So charge is moving in either direction. It's just which bit you're looking at. Cool. They are the same thing. Right. Electrolytes. This is awkward, and I'm sure you're familiar with them, but electrolytes are basically current moving through a fluid. It sustains that current movement by moving not just electrons, but ions as well. So that because the relative mass of these, well, it's not the relative mass, the relative resistance, isn't it? What I've used a nice term here. Relative motility. I like that. Do you like that? I bet you do. So the relative motility of these ions is low relative to them in a solid. So yeah, they move, but it's massive resistance compared to a wire, as you can imagine, because of the size of one of these things is huge relative to the size of an electron. It's going to be like really hard to pull it along, right? Ooh, look, it moves side to side. What drives the motion of that charge is, well, it's simple. It's charge, repulsion, and attraction. But more specifically and more scientifically, it's the difference in potential between one place and another place. Just like gravitational potential, if something's got lots of it and there's a place where there's less of it, they'll they'll go from there to there. It'll move in that direction, right? And we think about that in terms of a gravitational well, don't we? If we imagine like a well shape. If you're up high, you'll fall to the base of the well. And we thought about that when we were thinking about this in quantum. Now, in electronics, though, you've got positive and negative. So you've not only got wells, you've got hills. But ultimately, if you've got something on a hill, it'll try to get down to the floor. Just if you've got something on the floor, it'll try to get down to the bottom of the well. Now, it's not as simple as that either, is it? Because what really happens is that a well tries to eat a hill, and a hill tries to fill in a well, and that's why they're attracted to each other. And two wells wouldn't be attracted to each other because they're both trying to pull on the field the same way, and so they're going to push each other away. And two hills are going to try and distort the field in the same way and are going to push apart from each other. Whereas the these guys are going to collapse in on each other, and that's why they're attracted to each other. Nice image. I like that. Thought it was nice. But anyway, before we go too deeply into the voltage stuff, do you remember I equals naive? Right? It's an important thing, isn't it? Current is proportional to number density, which is the number of free charge carriers per meter cubed. A, cross-sectional area of the conductor. V, drift velocity, which is like the average velocity of every every charge carrier moving along the wire. It's actually really slow if you remember. It's like 10 to the minus 5 meters per second. Pretty slow. Number 4 is the electrice charge, which I have spelt wrong there. That's hilarious. The electric charge. Usually E, but in an electrolyte, it could be the charge from an ion, but to be fair, you'd never do that. Then we've got Kirchhoff's first law. Basically, the sum of currents entering a junction is equal to the sum of currents leaving a junction. Pretty obviously, if 10 goes in, 10's got to come out. You all know what you do with that. Now, it can get a little bit difficult when you merge these ideas, where you can think about, for example, number of charge carriers. You can merge that with the ideas of density, volume, and Avogadro's number. And we have practiced those in class, haven't we? Where it's like, ooh, here's copper. Copper has a molar mass of 65. I think it's 65. And then it's got a density of a lot. Determine some factors about it, right? We've done them, and in reality, you're probably only going to get a question like that on unified, unless it's like step by step for you, like the one below. So if you read this, well, I'll read it and pause the vid and have a go at it, and then I'm going to do a video where I show you how to do it. Hopefully, you don't need to watch that because I think we've done this a few times. So a block of copper with a density of 8,960 kilograms per meter cubed and a molar mass of 64 grams is shaped into a block of 1 centimeter by 1 centimeter ends and a length of 20 centimeters. How many moles of copper are present? If the number of free charge carriers is equal to the number of copper atoms, how many free charge carriers are there? And what is the number density of copper? And if a current of 3 amps is sustained in the copper block, what would be the drift velocity of its free electrons? And yes, I was pausing because once again I've made a little error there where I haven't put a question mark. So pause it, have a bash at that. Awesome. Yes, so back to this then. EMF and PD. These are the driving force and the removing force of the energy within the circuit. But basically, they are voltage, aren't they? It is a measure of the energy transferred per unit charge. EMF, though, it is to electrical charges, and for PD, it is from electrical charges. So energy is being given to the circuit, it's EMF. If it's being taken out of the circuit, it's PD, right? So we get this nice equation that voltage or potential difference is equal to work done per unit charge, or energy transferred per unit charge. It's also a nice way for us to determine the work done on a charge moving through a potential, which is work done equals the magnitude of that charge times the change in potential that it moved through. And that's also how we get to the electron volt. An electron moving through a volt does 1.6 times 10 to the minus 19 joules of energy. And there you go. That's an electron volt. Useful unit for dealing with tiny energies. Resistance then, just like with force, you do a force, you get acceleration. This is mitigated by the mass. Big mass, small effect. Small mass, large effect. EMF is exactly the same thing. With current, EMF provides the force, that's why we've got electromotive force, and it produces a current, but that's mitigated by another factor like mass called resistance, which you've heard of before, because this is a recap. Like I'm stopping. You can combine this with the ideas of energy and produce some other useful energy, other relationships, other equations. Work done per unit charge equals current times resistance, and then you got work done equals current times resistance times charge, and then loads of things that can come out of that. You need to sort of be able to mess around with that, which you can because you're capable A-level students. Right, Ohm's law. Ohm's law states that voltage is directly proportional to current for an ohmic conductor at constant temperature. Right, it basically means a straight line on an IV graph. that is a weird rule, really, isn't it? It's like, oh, here's a law that only applies for my things. It's like saying Liam's law. Liam's law is that everything goes my way when I say it does, in the conditions when everything has already gone my way and I've already said it. It's like obvious. Anyway, get a real law, mate. Anyway, IV characteristics. You need to know these. If it's just ohmic, we call that ohmic. It's I is V is proportional. It's an ohmic conductor, which means it's a wire or a resistor. You could be a filament bulb where your current tapers off as your voltage increases. That's because of an increased resistance due to heat. Um, and a diode works slightly differently, doesn't it? You increase voltage, you get nothing, 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 and eventually you get loads. That's because it's sort of provided them with the energy required to cross that gap. And as soon as they've got that, they've got no additional resistance to their motion. So a diode is like a filter for weaklings. Get out, weakling. But if you're not weak, go. Oh yeah, also before I carry on, um, if you that's called forward bias. A reverse bias, which is like using it in the wrong direction, takes much more voltage to make the opposite happen, but it will happen, but like right down that side. This is hard to choreograph. There we go. Doesn't make any sense. Resistivity, resistance times cross-sectional area over length. Resistivity is a constant for a material at a constant temperature. Resistivity does much like normal resistance does. It goes up if it gets hotter, because if you heat something, its cross-sectional area and length aren't going to change massively, but its resistance will. So resistivity goes up with temperature as well. You know this formula, and once again, you can make it more complex with the introduction of density, which a couple of the questions that I've set you will. Then we've got electrical power, which is you need to be able to derive this by combining V equals IR, V equals W over Q, and I equals Q over T. You get energy equals current times voltage times time, and then you get power equals current times voltage. That's the simple format of it, but you could be asked to do that in an exam. You can also combine V equals IR and that, and you can get those two equations here and here, right? Really useful, these equations, but it is possible to mess up with them. For example, if you're given like the supply voltage of something and then you're asked to work out the power used by a resistor, you need to remember the power used by the resistor is the V in that equation is the V for the potential difference across the resistor, not the total voltage. So it seems obvious now, but I'm sure someone has made a mistake with it. I know I have. I know people have. And there are complicated questions where it's like, here's a power station, it's 200,000 volts, and then it'll be like, how much energy is used per second in a meter of this wire, but people use 200,000 volts, but actually that doesn't apply because it's over the entire length. And if you don't know the length, then you can't know. Do you know what I mean? You'll need to know something constant about it, like its resistance and its current moving through it. But there you go. Cool. So that's the essential basics. Those are the things that are just like, they're the current basics. You need to know those. And then you need to be able to apply them to the more complicated ideas of parallel series complex circuit analysis, which boils down to calculating total resistances in simple series, simple parallel, and then mergers. Then potential dividers, internal resistance, and sensor circuits. That's it, really. It's really quite simple. So, series and parallel, right? You know what they are. They follow different rules. Kirchhoff's first law always applies. Kirchhoff's second law always applies. Kirchhoff's second law states that the closed circuit loop, the sum of EMFs are equal to the sum of the PDs. It's a statement of conservation of energy, which basically means in a parallel loop, in a parallel arm, 5 volts goes through that, 5 volts goes through that. I should say across, 5 volts across that, then there'll be 5 volts across that if they're in parallel with each other. That's because any charge carrier will not necessarily, won't be able to go through both paths. So whatever potential difference there is between this side and that side will be the same no matter what path you took to do it. Cool. So then you need to know how to derive but you don't need to remember them because they're provided for you, but you need to know how to derive